Thanks, Andrew. So for many years now, and it's been many years, I've been asking myself this one simple question. What is the origin of form? How do we invent form? Where do we begin? How do we think of generating a product, a building, a city, a piece of clothing? How do we start to think about this process? Is it a preconceived image of a narrative? Do we design form by immaculate conception, intelligent design? Is it a matter of getting rid of the stone that is in the way, as Michelangelo once pointed? Or perhaps it is an idea about technology and optimization and function. But if indeed form is to follow function, how is that function tested, evaluated, validated? According to whom and by which criteria? This is Ant Farm. Pneumatic structures for the naked. And so it has been my assumption that design by shift of perspective may be considered perhaps a second nature. And it is in the prospect of this natural way of making things that I've, over the years, accumulated a set of design research experiments with the aim of formulating a new design approach that is inspired by nature. And so the pioneers of such a design approach are few, but like Buckminster Fuller and like Frei Otto, they're immense, immense in stature. And so those are my heroes, my 99. They were the form finders of the 70s, and they've asked themselves not what an object wants to be, but rather, what does a material want to be? What does an environment want to be? Those were the generation of designers that developed a hands-off approach to design. And it is in the spirit of such intellectual predecessors that have left us with this legacy of a natural way of making things that has profound implications of the way in which we make things in the world today, and also great significance as to how we perceive this set of ideas about sustainability. And so how do we begin to think about natural design? So I began by searching for answers in nature, and it was early on when I discovered that nature authors not forms, but processes to think about form. Recipes that mix material and environment together, and it is due to those mixtures and those relationships that form emerges. So I began collecting and mapping and classifying all sorts of types of precedents and procedures, and this is essentially a one-liner of my entire PhD dissertation. And I've developed a method called computationally enabled form finding, which has to do with bringing together material properties and environmental constraints, mixing them together, and then generating form out of them. And so the idea is that a designer could then approach those tools and use them in different ways. He becomes an editor of constraints. And so instead of designing 2- or 3-dimensional forms and then sending them off to the engineers for analysis, whether structural analysis, environmental analysis, and optimizations, traditional ways that we're thinking about design, the idea here is to ask, how do we put design on its head? And we start from analysis. We start from the environment. We start from material properties. And we generate 3-dimensional form out of this process. So before we moved into computational algorithms, just a few words about what can nature do for us and what can't it. So I wanted to focus on 2 of nature's greatest features that have been a great inspiration for my work, have always been and will always remain. And those are those following 2 features. The first one is that nature is a grand material engineer. We already know that it can generate abalone shells, which are twice as tough as our high-tech ceramics, and it can generate silk, which is 5 times stronger than steel, so it knows how to organize matter. Nature also designs for the multifunctional. A leaf structure can support itself structurally while at the same time converting light into sugar in the process of photosynthesis. This is our day lunch, I've heard today. Also, our muscles support ourselves mechanically, but at the same time they manage and conserve our energy. But there are a lot of things that nature cannot do. It is so arranged that trees do not grow into the heaven. This is from Goethe's Life and Poetry. And why can't trees grow into the heaven? Well, because nature has not invented pumps. We humans have, and this is why we have the skyscraper, right? Nature hasn't worked with wheels either. We use wheels for movement. Nature uses other mechanisms for movement. But interestingly, it's precisely those criteria, mass production versus nature mass customization, or uni versus nature multifunctional design, that the Industrial Revolution rejected completely and up to this date. And so I grew up with this image. My parents are both architects, and my dear father presented me with this image many, many years ago. This is the first glass skyscraper maquette by Mies van der Rohe from the 1920s, and it's sort of the antithesis of my reason for being here in this world, which is the separation between materials and functions. So there is steel. Steel takes care of the structural performance of the building, and glass is assigned the environmental performance of the building, right? So separations of materials to different disparate functions. So we beat nature in size and speed to a certain scale range, and you'll hear more about how we don't by church. But there are a lot of things that we harm our already injured planet because of those pumps and those wheels, right? We waste steel, we waste oil, we increase our carbon footprint to an unimaginable rate. And so the next question is, how do we begin to think of a natural way to design that uses and utilizes those principles of nature, but in scales that match human production and that embrace technological advancement? Can we think about a Nature 2.0 initiative? What does it mean to beat nature today? What does it mean to design in a sustainable way? And so, if you understand this image, you'll understand my entire work. This is a membrane of an eggshell. This is how nature makes things. And like most objects and artifacts of Mother Nature, it's made of fibers. The fibers are articulated in such a way that they distribute the loads equally on the surface area of the eggshell, while at the same time, so this is the material engineer, while at the same time, multifunctionality, they allow for food absorption, heat exchange, etc. So there's a lot of functions that are incorporated just by controlling those materials and designing them. And so in the spring of 2008, I've been approached by Paola Antonelli for her show, Designing the Elastic Mind in MoMA. And she asked me to design 4 new objects for the show. I was terribly excited, but I decided instead of designing 4 objects, I would design 4 processes. So instead of designing 4 objects or 4 forms, I would design 4 processes for the generation of form. The underlying theme for the generation of those processes was exactly the idea of multifunctionality. The idea that a structure can sustain itself structurally, but can also conduct heat or conduct thermal gain. And so remember Mies, again, the antithesis of Mies. We're moving onwards towards designing and engineering systems that incorporate performance criteria. And so monocoque was my first project. It stands for French, a structural skin from the avionic industry. And the shear stress line and the surface pressure are embodied in the surface by the allocation and the relative thickness of those vein-like elements that are built into the skin. So this structural skin was 3D printed, much like we do 2D printing, but just 3D printing three-dimensional objects from two materials. The black, dark material is stiff and cares for the structural performance of this building skin. And the white material is soft, it lets light through, and it lets temperature and heat exchange through. So again, the designer, as he or she is designing, can manipulate the thickness of those vein-like elements depending on the type of load and the direction of that load. Fate maps was an experiment in reconstructing natural tissues by controlling fiber directionality. So you start from micrographs, from biological specimens. You understand how material behaves, and you scale up this behavior not only in dimension, but again, in terms of its physical articulation of the fibers. This is a butterfly scale. And as much as nature sculpts sand and soil with air and with water, ray counting was a project that the theme of which was sculpting with light. And so the designer can control the thickness of this translucent surface by relating it to constraints of light performance, by deciding how much shading he or she desires in a certain space. So the designer, again, becomes kind of a gardener, an experimenter that generates lots of options. Clearly, a glass house in Iceland would behave in a completely different way than a glass house in the Sahara Desert. And so we're generating lots of options, just like our melanin skin tone changes in different geographical locations. We're generating different options, we're eliminating them, and we're working towards environmental fitness. Now, environmental fitness is an idea that nature knows very, very well, and it is pronounced in a very elegant way in the human bone. The human bone has the capacity to modulate itself as it is alive, to remodel itself according to structural loads. So it was Julius Wolff who discovered in the late 19th century that the bone has this capacity, while stimulated with additional weight, to build more little beams, more trabeculi, more calcified structure, and to change its structure as it's moving. So it's doing the analysis, the modeling, and the fabrication in one process. We don't. We separate between modeling, analysis, and fabrication. And so when we go to outer space, we lose bone tissue. When we become pregnant, we gain this bone tissue. And so the bone knows exactly how to adapt its material organization, how to work towards multifunctionality and customization, depending on the type of load. So, okay, so now that we sort of understood those major general and abstract ideas, how are those ideas from the world of art and from the world of design come to portray themselves in more practical applications in the medical industry, but also in technology? So I always ask not what science can do for design, but what can design do for science? So what can design do for science? What can design do for technology? So we know that we can, using those algorithms today, we know we can map load. We know that we can map heat. We know that we can map light. But what about the medical industry? Can we import some of these understandings to design better medical devices? And so what about the mapping of pain? And so pain is this personal thing, and it's different between individual and individual. It has always been difficult to map, and it has always been poorly treated by the medical industry, especially Western medicine. And so here the idea was to come up with a project that is a process that I call second skin. And the idea of second skin is basically to map the pain profile of a particular patient and to distribute hard and soft materials depending on his or her anatomical or physiological pathologies. The project was inspired by animal coding patterns, only instead of color, we're now controlling stiffness graduation. So instead of the different colors that emerge for those animals, we're controlling the material properties. And I've been lucky and honored to collaborate with Professor Craig Carter from the Department of Material Science at MIT on this project. So we've designed a protective glove against carpal tunnel syndrome. So for those of you who know or don't know, carpal tunnel syndrome is the syndrome, the condition of which the median nerve is compressed at the wrist, and it leads to weakness, to pain, to muscle atrophy. And so here the idea was that if we could map the pain profile of each patient, we could then affect and customize the glove to this particular pathology. The problem with immobilized braces in today's industry is that because they're mass produced, they're often too big, too small, too constraining in terms of movement. And so is there a way to then map the specific pain profile by unfolding the skin, literally, of your wrist, well, not literally, but digitally, and then reformulating this pain profile as a set of graduation of stiff and soft materials that would cater to hold and allow you to constrain the movement in a flexible way. So these are the gloves. I fell off my bike yesterday, and I'm a vivid bike rider, and so I'm waiting for my gloves to be printed. This is a zoomed-in view that shows you that every molecule, metaphorically, in this glove, again, the question of dynamic range, how do you define one component in the glove which reacts to pain, is very important. And so the idea that one molecule equals one bit almost in terms of its behavioral capacity is very, very important here. And so this is, you're looking at the first prototype, which will be displayed in a couple of days in the Museum of Science. Similarly, BEAST was a project to generate a customizable chaise lounge, which is made of one material. It's 3D printed. And this material changes in thickness, but it has different material properties. It has different mixtures and different compositions. So it sustains, it holds itself structurally, while at the same time it accounts for certain physiological pressure points of the user. And so think of wearing your acupuncturist or wearing your massage therapist to work. And so these 5 materials change color. The darker, the stiffer, the lighter, the more softer. There are also silicone bumps that are attached to the skin of this chaise. All right, so medical industry product design. How do we, instead of using those ideas and importing them to products that are useful for us as humans, how do we now reconsider how we reinvent our technologies for construction? So it was Louis Kahn who said, consider the momentous event in architecture when the wall parted and the column became. For me, the wall and the column, as for nature, is one thing. It's just a matter of how material redistributes itself to cater for those different conditions. And so the idea was how to now take some of those ideas and generate a new technology that would cater for a more sustainable way of making and doing things. And so we know that if 50% of new commercial buildings were built with 50% less energy, we would be saving 6 metric million tons of CO2 for the life of buildings. Can we print buildings as if we were 3D printing bones? Can we save that 50% of material? Yes. So now, a brand new invention of mine at the MIT Media Lab is development of this new technology. It's called variable property printing. And the idea of this technology is to allow one to map those structural conditions and generate variation in porosity and variation in elasticity to generate this effort in material efficiency. So we would be printing buildings as if we would be printing oysters 100, 1,000 times their scale. We would have one material, we would vary its properties, and we can control soft and stiff materials, opaque and translucent materials. I wanted to end on this one note, commemorating the power of design today. I was thinking that whenever we think of a momentous world problem or a persistent threat that is posing to harm humanity today, whether it's poverty, whether it's climate change, whether it's the medical industry, whatever solutions, ingenious solutions are generated, they have always and will always consist of design. Design is truly alive because it's truly, truly relevant. As we move in this moment of transition, not in the receiving end of change, but in the sending end of change. And it's high time that we've transcended the fallen state of design from the sanctuary, the dinosaur sanctuary of style, into a new and exciting paradigm of making, literally making our future. And it's happening. So thank you.